In this video, we'll be discussing the architectural design of software systems. Recall from last lecture that the design model was comprised of 4 elements: class design, architectural design, interface design, and component level design. Today we'll be exploring the architectural design elements. These describe the structural parts of the system, their interfaces, and the behavior of individual components. So without further ado, let's get into it. When you first hear the words architecture, you probably think about building architecture. And when you want to start building a building, you have to start with a plan. Before we start building, we need to have a unified vision, know what materials we'll use, what rooms the building will contain, and consider the overall shape and outside details of the building. And of course, how it will interact with the environment around it. But architecture is more than this. It's also the manner in which all the various parts or components of the building come together, and how the rooms will interact. Notice, however, that it does not go into detail about what furniture will be in each room, or what each room will specifically contain. The focus rather is on how the building will be subdivided into rooms, and how these rooms will be connected together. Architectural work products are representations such as floor plans, 3D models, and so on to document these features of a building. Well, software architecture is no different. Before we start designing the individual components of our software, we need an overall plan or blueprint to make sure it all comes together correctly. We need to document what components we'll have and how they'll interact without necessarily going into implementation level details about these components. Instead of blueprints and 3D models, we use tools such as component diagrams, class diagrams, and communication diagrams to document our work and plan the architecture of our system. So what is software architecture exactly? Well, our textbook definition is that the architecture of a software system is a comprehensive framework that describes its form and its structure, its components, and how they all fit together. The idea here is to create high-level representations that describe the components in the system and the interfaces they'll provide to allow communication with other components. These representations allow developers to analyze the effectiveness of the design in meeting its stated requirements, to consider what architecture alternatives are at the stage where making design changes is still relatively easy, and reduce the risks associated with the construction of the software. Okay, so I've mentioned components a few times now. So what is a software component anyway? Well, it's a modular, deployable, and replaceable part of the system that encapsulates implementation details and exposes a set of external interfaces. That was a bit of a wordy definition, so let's break it down a bit. A component is a subdivision of a larger system that breaks the complexity of a system down into more manageable parts. The idea being that it's easier to solve and understand smaller, more manageable problems than trying to take on one large problem as a whole. Next, components hide implementation details. This is what we mean by encapsulation. Other components in the system should have no view or dependency on the implementation details of another component. Rather, they should communicate through a standard interface. Beyond providing information hiding, this information also allows for components to be swapped in and out with no changes to other parts of the system, so long as they share a common interface. This is what we mean by modular, deployable, and replaceable. There are a few different ways we can view what exactly a software component is, and this is largely dependent on our overall design philosophy. In the object-oriented view, a component is a set of one or more collaborating classes that work closely together. In the simplest case, it may just be one class which encapsulates implementation details and the attributes of the class and provides an interface via its public methods. In other cases, it may be a more complex set of classes that share a set of common interfaces. In the traditional view, such as in languages like C, that lacks classes and objects, a component is a functional element of a program that incorporates processing logic, the internal data structures, and all interfaces. This is often called a module. In C, a component could be as simple as a C file that contains specific functions and data structures, and a header file that provides an interface for this component and hides implementation details. In the process-related view, components are pre-existing, off-the-shelf, prepackaged components, or design patterns. This approach assumes that components are not being created from scratch, but rather that existing software components or design patterns are being chosen from a catalog of proven designs. The focus here is instead on choosing the correct components to use, rather than designing their interfaces and responsibilities ourselves. So why is software architecture so important? Why can't we just skip this step and start designing the internal workings of our components? Well, there's three important reasons. First, the representations we create while designing the architecture are an important tool for facilitating communications with our stakeholders. These representations allow us to get early feedback about the overall architecture of the system before we fully commit to it. Making changes at the architectural level later in the project could be devastating in terms of costs and risks. Which leads us to the next point. These early architectural design decisions have profound impacts on all following design work, and eventually implementation work. Getting them right now and keeping a consistent overriding vision of the system will save time later in the design process and prevent future rework. Lastly, as we've spoken of before, breaking a problem into smaller problems makes it more intellectually graspable. Subdividing a system into components will make it easier to understand, and an easier to understand system is one that's easier to build, easier to test, easier to debug, and easier to maintain. When we talk about building architectures, we often talk about different kinds of architectural styles. For example, here's a picture of Weldon Library and the inside of the UCC. Both are an example of a style of architecture called brutalism. Brutalism was an architectural style that was popular in the late 1950s and early 1960s, especially for government and university buildings. The style is characterized by minimalistic constructions that showcase the bare building materials, often concrete, and the structural elements over decorative designs. It was used by governments and universities due to its low cost and ease of construction. The point here is that this style is consistent throughout the building. Both the insides and out provide a consistent architectural vision. Another example on campus would be the Ivy Building, which we might describe as modern. But by far the most common style used on Western's campus is the collegiate Gothic style used on buildings such as Middlesex College and University College. So what does this all have to do with software architecture? Well, software architecture also has styles. For example, we have the data-centric style, data flow, main program subprogram, layered, and model view controller. We'll be getting into these in a bit more depth shortly. Each architectural style describes a system category that encompasses the following items: a set of specific components that perform a function required by the system, a set of connectors that enable communication, coordination, and cooperation among components, constraints that define how the components can be integrated to create the system, and a set of models that enable a designer to understand the overall properties of a system based on the properties of its individual parts. Just like with the building's architectural style, a software's architectural style dictates an overall vision of the system that impacts both its outward appearance and its inner workings. We'll now take a look at a few common software architectural styles. These tend to cover most software systems you'll encounter, but there are, of course, many other styles, with many more being created every day. The first is the data-centered style. In the data-centered style, a data store resides at the center of the architecture. This could be a database or other kind of data store, such as a file system, repository, or a blackboard. Components, namely client software, all access the central data store to update, add, delete, or otherwise modify the data in the store. These components can be completely independent and communicate solely through the modified data in the store. An advantage of this style is that components can be changed or added to the architecture without any concern about other clients, because everything works independently. The next style is data flow. In the data flow style, independent components called filters are used to transform data. Pipes define the connections between the filters that transmit the outputs of one filter to the inputs of another. In this way, vastly different overall outputs can be achieved by connecting filters in different layouts. Filter components themselves require no knowledge of other filters, making them easy to swap in and out as needed without significant changes being required to the system. Common application of this style is in data processing applications. You may also be familiar with this style from Unix-based operating systems, such as Linux, that use pipes to pass data between command line programs. For example, you might use the Unix cat command to pipe the text of a file into the grep command to find certain lines, and then further pipe that output into the wc command to get a line count. This allows for far more complex and emergent behaviors than any of the individual components can provide individually. Next up is the call and return style. The call and return architectural style aims for a program structure that's relatively easy to modify and scale. It's normally based on one of two substyles. In the main program/subprogram substyle, a program invokes one or more program components, which in turn may further invoke other components. You can think of this like a function or method call that may in turn call on other functions or methods. Then again, in turn, may call on other functions or methods. This creates a hierarchy of calls, starting with the main program as shown in figure 10.3 on the screen right now. The other substyle is remote procedure call, which is a similar idea, but the calls are made to components distributed across multiple networked computers rather than only on one device. This is an architectural style used in systems such as web services. Now here's one that you should be familiar with, the object-oriented style. As you know, in object-oriented programming, the components of a system encapsulate data and other operations that are used to manipulate the data. In most cases, these components are classes or collections of collaborating classes. Communication between components is achieved through passing messages by invoking public methods on the instances of these classes. This is a very popular style that is used by most modern programming languages. For example, it's used by Java, which we're using for our team project in this course. The next style is layered. In the layered style, layers are defined that provide services to the layers above it through operations completed by interacting with the lower layers. For example, the user interface layer might call on the application layer when the save button is pressed in the GUI, which in turn calls on the utility layer to create a file, which in turn interacts with the core operating system to actually create the bits on the hard drive. In this way, outer layers interface more directly with the user, and the inner layers interface with the operating system or underlying hardware. Intermediate layers provide utility services and other non-user interface related functions. We can see each layer as becoming more abstract as we go towards the outer layer, and containing more low-level or hardware-specific details as we go towards the innermost layer. The last style we'll be taking a look at is Model View Controller, also called MVC. This is a style that's very popular in web and mobile application development, but can be used for any kind of application with a user interface tied closely together to a data backend, such as a database. The MVC style is comprised of three different kinds of components. Models, which contain all application-specific content and processing logic. Views, which contain all interface-specific functions and handle the user interface. And controllers, which manage access to the model and view components, and coordinate the flow of data. As I stated earlier, there are far more styles that exist, and more are being created every day. This was just a small sampling of some of the most common ones. I should also mention that it is possible to use multiple styles at the same time. In fact, this is often required. For example, while developing an interactive e-commerce website, you might use the MVC style, but also the object-oriented style. On top of this, there may even be a further style applied if the same central data store was used for both the website and the retail point-of-sale system, to keep everything in sync. This would be the data-centered style. One thing to consider for your project is what architectural style you'll be applying, and if it is appropriate for the application you're trying to create. It's normally best to focus on one overriding style that will guide your design work, even if the other styles may play small roles. We'll now briefly touch on architectural patterns. Architectural patterns address a specific architectural problem and propose a solution that's been tested and developed by best practices. These patterns are used in conjunction with architectural styles to help shape and customize the overall structure of a system. At a high level, we could consider a style to be a collection of related architectural patterns. Each pattern focuses on a specific and common problem, and provides a description of a potential solution, as well as the limitations of that solution. These patterns are not normally code or ready-to-use components that you can just drop into your system, but rather they're high-level descriptions of a solution. We'll talk more about patterns in the coming weeks, and this is covered in a more depth in Chapter 14 of your textbook. A common question I get is what are the differences between an architectural style and a pattern? Styles apply to the system's architecture in its entirety, and patterns tend to focus on only one very specific aspect of the architecture. For example, we might be using an overriding MVC style to design a mobile application, but how we use web services to handle the communication between the mobile application and our backend might be based on a specific pattern relating to web service communication between a model component and a data store. Now, we can't just pick any architecture at random when designing our system. There are a number of considerations we have to make. Some of these include economy. Software often suffers from unnecessary features or non-functional requirements. The best software is uncluttered and relies on abstraction to reduce unnecessary detail. Visibility. Poor visibility arises when important design and domain concepts are poorly communicated. It should be obvious to the members of your team why these decisions were made. Spacing. Sufficient spacing leads to modular design, but too much spacing leads to fragmentation and a loss of visibility. We need to break things into components without introducing hidden dependencies. Symmetry. A system should be consistent and balanced in terms of attributes. For example, an architecture that requires construction of entities to be accompanied ultimately by their destruction is symmetric and balanced. Emergence. A good architecture should have self-organizing behavior and control. For example, many real-time software applications are event-driven. In these kind of systems, it's difficult to plan for every possible sequence of events. So we should create a flexible system that can accommodate any kind of emergent behavior that might occur. It's important to note that these considerations do not exist in isolation. They interact with each other and are moderated by each other. For example, spacing can be both reinforced and reduced by economy. That is to say, keeping our software system uncluttered and relying on abstraction can also help with separating concerns. Now, moving on to architectural design. As architectural design begins, the first task is to place the software into context. What is meant by this is that the design should define the external entities, such as other systems, devices, people, and other actors that might interact with our system. And we need to define the nature of this interaction. This information generally comes from the requirements model. Once the context is defined, the next step is creating a set of architectural archetypes. An archetype is an abstraction that represents one element of system behavior. Archetypes don't have enough detail to be implemented, but rather define a collection of abstractions that must be modeled by the architecture of a system. We'll talk more about archetypes in a second, but first let's explore how we represent the context that we just discussed. One of the ways we provide a visual representation of architectural context is with an architectural context diagram, also called an ACD. This is not a UML diagram, as UML does not contain any diagrams specifically for showing system context. But it can be helpful when used in conjunction with other UML representations to detail a system's architecture. And it looks something like this. In the center box, we have our target system. This is the system or part of a system we are creating. On top, we have superordinate systems. These are external systems which use our system to realize some function. On the bottom, we have subordinate systems. These are external systems that are used by our system to realize its function. On the right, we have peers. These are closely related external systems or other internal components on the same level. They both use and are used by our system. And finally, on the left, we have our system's actors. Defining all these elements in an architectural context diagram sets the context for our system and allows us to know its dependencies and what interfaces it must provide. Shown here is an example for the SafeHome security system case we've been following in our lectures and textbook. Here, the target system is the security function, that is, arming, disarming sensors, and responding to error and alarm events. The superordinate systems are the other SafeHome products and the internet-based system. The subordinate systems are the security sensors the system uses, such as door and window sensors. The peer systems are the camera surveillance function. And the actors are the homeowner and the control panel, but only if we consider the control panel to be an external device and not part of the system's security function. For example, the security system function would not be running on the control panel, based on this diagram. Otherwise, if it was running on the control panel, it would just be part of the target system. Now that we have covered context, let's get back to archetypes. An archetype is a generic model of some important component in the system. This might be represented as a class or pattern that is a core abstraction that's critical to the design of the system architecture. For example, in that SafeHome case, we might have an archetype named detector that is an abstraction that encompasses all sensing equipment, such as door sensors, monitor sensors, temperature sensors, and so on. In general, we normally don't need too many archetypes to define a system's architecture. A small set of archetypes can design a relatively complex system. We can figure out what type of archetypes we need by examining our requirements model, specifically the analysis classes that we've already discussed in a past lecture. Let's take a look at an example. What we're looking at right now is a very abstract UML class diagram that only shows basic relationships and class names. We can use this kind of diagram to show archetypes and their relationships between them. Each class shown here is an archetype in the SafeHome example. Let's review what we should already know based on our UML knowledge so far in the course. This empty diamond is aggregation. This relationship type means that a controller is made up of one or more nodes. The empty diamond symbol is generalization. This is how we show inheritance in UML. This means that the detector and indicator are children of the node archetype. The node archetype represents a collection of input and output elements. For example, a node might be composed of various sensors or have a variety of alarm output indicators. In our actual implementation, this might be a common interface that both our detector and indicator classes will eventually implement. A detector is an abstraction that can represent any sensor equipment feeding information into the SafeHome security function. This could include door sensors, window sensors, motion sensors, temperature sensors, and so on. An indicator is an abstraction that represents any device that can indicate an alarm or an air condition. This might include lights, sirens, or other outputs. And lastly, a controller is an abstraction that allows for arming and disarming of a node. The controller resides somewhere on our home network and has the ability to communicate with other controllers. As the design of your architecture proceeds, you further refine these archetypes. For example, in the case of the SafeHome system, we might now refine the detector archetype into a sensor class hierarchy. In this example, a sensor class is created with a child class for each sensor type. The sensor class itself might implement a node interface that is common to both detectors like sensor, as well as any indicator classes we might have in our system. As we refine archetypes into components, the structure of the system begins to emerge and become more defined. But how do we choose these components? First, we begin by defining the analysis classes we identified as part of the requirements model. These classes represent the entities within the application domain that must be included in our architecture. The application domain consists of the components that relate to the core business logic of the application. Next, infrastructure components need to be identified that are required for the application to function, but are not part of the application domain. These would be things like database components, network communication components, task management components, and so on. These types of components belong to the infrastructure domain, which consists of components that support the application software. These tend to relate to low-level hardware, network, system software, communications, and database components. Now let's take a look at the overall SafeHome architecture. And one way we can represent this visually is with a component diagram. This is a new UML diagram that we haven't looked at too closely yet. So let's go through some of the parts. Currently, the highlighted element is a component. These are drawn as boxes and either have two smaller boxes on the left or a box with the component symbol that looks something like this. The two boxes on the left style is from UML version 1, and the component symbol in the right corner is the notation used in UML version 2. It's still common to see both styles today. The dotted lines drawn between the components are dependencies. Recall that dependencies are directional relationships which are used to show that some UML element or set of elements requires, needs, or depends on other model elements for specification or implementation. In this case, they depend on an interface provided by another component. This example component diagram from our textbook is a little bit simplified and still very abstract. Component diagrams can also show more details about the interfaces provided, for example. Now let's take a look at what this component diagram is telling us. First, we have an external communication management component. This component acquires and processes transactions as they move from the user-facing components, such as the GUI and the internet interface, and calls the SafeHome executive component to complete its functions. The SafeHome executive component manages the information and selects the appropriate product function based on the transactions passed to it from the external communication management component. For the sake of this example, let's say it's calling on the security function. Under the security function, we have the control panel component that processes physical input from the homeowner and calls on the security function to arm and disarm the system. We have the detector management component, which communicates with the sensors and relays alarm conditions to the security component. And lastly, under security, we have the alarm processing component that deals with alarm states. As a quick summary, these types of component diagrams are used when you are dividing your system into components and want to show the interrelationships through the interfaces or the breakdown of components into lower level structures, as we sort of see here, with how security is broken down into subsystems. This architecture is still at a very high and abstract level. Before implementing it or moving on to component design, we would have to refine the architecture further. This would be accomplished by applying the architecture to specific parts of our problem and trying to uncover additional details, structure, and components that might be required to address each problem. For example, after elaborating on the SafeHome security functions, we might arrive at something like this, with more detail on each security component and sensor type. The important things here is that we are still not providing details on the internal workings of the components. This is left for component-level design, which we'll be discussing in our next video lecture. One last thing I'll leave you with today is that, like all work products, architectural design should be subject to technical reviews. This involves assessing your architectural design for compliance with your quality requirements and identifying any potential risks with your design. By quality requirements, we tend to mean the non-functional requirements such as scalability, performance, usability, and security. These types of reviews are important as they have the potential to reduce project costs by detecting design flaws, issues, and risks early in the project, as well in the design phase, rather than after the design has been finalized. This reduces the chance of expensive design rework or refactoring later in the project. Architectural reviews typically only involve the development team as well as independent architecture experts. They make heavy use of architectural checklists, prototype evaluation, and review of architectural representations and diagrams. You can find an example of an architectural checklist under the supplementary information section on the Week 6 page on OWL. That's all I have for you in this video. Our next lecture video is going to be about component level design, and we'll start talking about filling in the details of those components we discussed in this video. Thank you for watching, and have a great day.